Yeah, so let us begin the class. I think my screen is visible to you and my voice is also audible.
Yes, sir.
Yes, sir.
All right. So in the previous lecture, we had seen some combinational logic designs based on this, static CMOS inverters also, and then some other non-conventional designs. For example, the pseudo NMOS and the depletion load NMOS based devices. And then we also saw the effect of multiple threshold drops which was happening when cascading, the pass transistors based logic designs. Okay. And we then also talked about the dynamic gates. Okay, so the dynamic gates, we saw that in the dynamic gates we have a pull down network which is composed of only NMOS. Okay. And then you also have two extra MOSFETs. One is PMOS and the other one is NMOS. And the clock is fed to both PMOS and NMOS. And the inputs are fed to the pull down network, which is composed of the NMOS. Okay. Now, there is a problem when you try to cascade such dynamic gates. Okay. Maybe I'll show you an example of dynamic gates. For example, here. So this is a dynamic gate. So where the pull down network is being implemented by these two NMOS. And then apart from these two NMOS, you have extra two MOSFETs, that is one is PMOS and one is NMOS. And both of these MOSFET, that is PMOS and NMOS, you feed clock into the gate terminals. Okay, so that was the dynamic gate. So now the problem is with cascading of these dynamic gates. So when you try to cascade in maybe such a fashion. Okay, so here is a one gate which is cascaded to the other dynamic gate. Okay, so the problem here is, suppose the output here, that is out one, for the first cascade gate, this cascade gate, the out one here. So this makes, suppose, a transition from 1 to 0. Okay. Let me take a pointer over here. So let us say that out one is making a transition from 1 to 0. Okay. So let's say that this is making a transition from 1 to 0. Okay. So now when this is making a transition from 1 to 0, so obviously that means we are trying to bring this out one to 0 via this path. That is, these two MOSFETs are on. Okay. So that is when clock is high. So it enters the evaluation mode. So out one should be 0. Right. So when out one is 0, so obviously that means this transistor should be off. Okay. So this transistor should be off. So that means my out 2. So that should maintain a status of high. Right. So out 2 should maintain a high status. When out 1 is low, so when out 1 is low here, that is 0. So this transistor is cut off. So my out 2 should maintain a high status, because during the pre-charge cycle, that is when my clock was 0, yeah, it has two phases, that is pre-charge and evaluate. So in the pre-charge, when clock is 0, the output node, that is out 1 and out 2, both are charged to full VDD. And in the evaluation mode, the pull down network is on, that is when clock is 1. So this node out 1, so this becomes 0. So when this becomes 0, out 2 should not become 0, or out 2 should not degrade from a high value, right? Because out 1 was already pre-charged to 1, logic 1 or VDD, right? So this is a problem here, that when out 1 makes a transition from 1 to 0, the out 2, so this also starts discharging. Okay. So this is because of the finite propagation delay of this network, right? So that is RC delay of this network. It has some delay. So because of that delay, the out one, that is TPHL, so it exists here, that is out one takes some times for discharging from 1 to 0. So because of that time taken by out one to go from 1 to 0, out 2 also starts discharging. Okay, so this is one of the problems here in cascading such gates. So that can also be seen over here. So for example, my input is this, and the clock makes a transition from low to high. Right? So clock is making a transition here at this point from low to high. Okay. So when the clock is making a transition from low to high, so that means at this point, this NMOS, So this is on. So my pull down network is activated. Input is already high here. So clock 1 comes up, clock 1 becomes high, clock becomes high. So this network is on. So out 1 starts discharging via this path. So that is being shown over here. Out 1 starts discharging. Okay. Now because of this propagation delay, I mean this discharging is not instant. So 1 to 0 is not instant, right? So it takes some time for this pull down network to discharge out 1 from 1 to 0. So because of this, I mean out 1 is discharging, so out 2 also starts discharging, right? Now when this out 1, that is this point, so this out 1 voltage when reaches VTN, so then at that moment this transistor shuts off. Okay. Otherwise this was earlier on. Yeah? So it was on because out 1 was at high voltage, so this was on. Okay. Now when out 1 reaches VTN, that is this point maybe. Okay, so this is VTN, let us say out 1 reaches VTN, this transistor turns off. Okay, so out 2 now cannot discharge further below this point. Right? So out 2 maintains now a value which is only equal to this point, right? This. Now earlier the value of out 2 was this much, right? So this value is actually lost now. So this cannot be retrieved in such circuit because all these outputs, so they are stored on temporary elements. That is, we store the outputs on capacitors, some capacitors, and those capacitors need to be refreshed in dynamic gates. So these are not static gates, these are dynamic gates where output is stored on some capacitors, and those capacitors have to be refreshed, right? Now since now out 2, which was earlier this much, now this has become this much. Okay, that is, it has reduced by delta V. Now the original value of out 2 cannot be retrieved in this circuit. So that is the problem here, right? Because whatever refreshing now you will do to the capacitance which is existing over here, so you will try to refresh it by some clock. So now that capacitor will hold only this much charge, that is this much charge total, right? That is this much voltage only. So this is lost. The actual output levels are lost. So this is one of the problems of the dynamic gates. Right? So this does not happen in the static gate because static gates, they can supply the same output till the power is supplied to them. But since here in the dynamic gates, the outputs are stored on temporarily on some capacitors which need to be refreshed by some clock mechanism. Okay, so because now the out 2 that is actual level has changed from this level to this, so in the next clock cycle only this level will be refreshed. So this is lost. So this is one of the problems of these dynamic gates or cascading dynamic gates. Now to overcome this problem, okay, so one can what one can do is one can ensure that during the pre-charge phase all inputs to this pull down network, so those are all 0. Okay. Right. So to overcome this problem which was existing here in the dynamic gate, what one can ensure is that all inputs to the pull down network are set to 0. That is inputs to the pull down network 2. This is pull down network 2 over here. Right. So all inputs to the pull down network 2 are if set to 0, then this problem can be overcome. Right. So if all input, that is input to this NMOS, is set to 0, then it cannot discharge to this value, that is delta V discharge is not possible. Okay. So this is one of the solutions. So how is it done? So this is done by including an extra static CMOS inverter in between the cascade. Okay. This is cascade of dynamic gate 1, and this is dynamic gate 2, pull down network 1 of dynamic gate 1 and pull down network 2 of dynamic gate 2, and in between the cascade you put a static CMOS inverter. Okay, so that the input of this pull down network is set to 0 when the output of this network is charged to 1, that is during the pre-charge phase. During the pre-charge phase, that is when clock is 0. So that is the pre-charge phase. When clock is 0, during the pre-charge, so this node is charged to 1 or VDD. Okay, so this node is also charged to 1, that is VDD. Okay, but the inputs of the pull down network 2, so those are set to now 0. Okay, So that can be seen here maybe. Let me remove all this. Right. So during the pre-charge phase, the output is set to 1, out 1. So because of this inverter, the input to this pull-down network is 0. So that means this pull-down network is never on during the pre-charge phase. Now during the evaluation, that is when the out 1 makes a transition from 1 to 0. Okay? So out 1 is making a transition from 1 to 0. So that is called the evaluation mode. Okay? Now, yeah, so this ensures that domino gates, they are set to 0 at the end of the pre-charge period. That is, the pull-down network inputs are set to 0, and this is only possible when you make a addition of inverter in between these two. Then one can also think of making a keeper MOSFET. So that can be brought here because yeah, so this can also be put here, so that this node, so that can be charged to full VDD. Okay. So that can also be ensured. Okay. So some of the properties of domino logics are mentioned over here. So one of the property is that these domino logics have very high speed, and they have smaller areas than conventional CMOS logic, and parasitic capacitances are small, so that higher operating speeds are possible. Now only non-inverting structures are possible because of the presence of inverting buffer. Yeah, so because of the presence of this buffer, only non-inverting logics are possible. And then charge distribution may of course be a problem. So we had seen what is charge distribution. So that can be a problem here because these node capacitances, or maybe the internal capacitance and internal node capacitances in the pull down network. So that may be associated with the drain diffusion capacitances. So during the pre-charge phase, one has to also think of charging the internal node capacitances in the circuit. Right. So charge distribution and charge sharing problem can exist in this domino logic also. Okay. Now apart from this domino logic, one can also think of implementing cascading the dynamic logics, and in this case you do not need an inverter over here, that is static inverter that we were using earlier in the domino logic. So that is being removed now. So that is possible by cascading two dynamic circuits in which one of them has a pull down network composed of NMOSes, and other one has a pull up network which is composed of PMOS. Right. So earlier we had both networks which were pull down network while cascading the dynamic gates, but yes, it is possible to cascade two dynamic gates which have two different types of network, that is pull down network and pull up network, using NMOS and PMOS are present. So you don't need a static CMOS inverter to cascade them. The only change you make here is that now you supply earlier we were supplying clock to both the cascades. Now we are supplying clock bar, that is this clock bar is supplied to the cascade which has a pull-up network composed of PMOS. Now this kind of circuit is called NP-CMOS logic circuit. Okay. And this is just a one way of cascading the dynamic gates. Okay. Yeah. Now this NP-CMOS logic, so this is also called zipper logic, and this DEC alpha microprocessor, this uses NP-CMOS logic. So this is one of the applications. Now one has to also think about sizing the pull-up networks to equalize the delay of the pull-down networks. So that one has to see. So it's a ratio problem. Now really dense layouts are possible with very high speed. So these are normally 20% faster than domino with correct sizing of pull-up and pull-down network. And this will offer you reduced noise margin. So reduced noise margin was seen with any dynamic gate. You will see that VOL cannot be 0. So dynamic gates have this problem of reduced noise margin. And the other important thing you will notice here is that it has two clock signals. Okay, that is clock and clock bar. So that is one of the bottlenecks here. That is you have clock and clock bar, both have to be supplied, and these clock and clock bars, so these two have to be non-overlapping. So if they are overlapping, then the correct functionality of this entire circuit cannot be ensured. So these have to be non-overlapping. So what is non-overlapping and how it affects the circuit functionality, maybe that we will study later on, maybe either today or maybe in the next lecture. So I think we are done with this combinational logic part of the syllabus. Now let us come on to the sequential logic design part. Okay. So let us talk about the sequential logic circuits. So I hope my voice is audible to you and the screen is also visible.
Yes, sir.
Okay. So let us talk about the designing sequential logic circuit. Okay. So how to design sequential logic circuit. In fact, let us first talk about the sequential logic circuits. So we had seen that in the combinational logic circuit, the output depends only upon the present inputs in the combinational logic circuit. However, in the sequential logic circuit, the output depends on present inputs also and the previous output also, or what we call as the output depend on present inputs and the current state. So current state depends upon the previous inputs. Okay. So this current state is again taken as a feedback from the output and again fed back to the input. Right. So output depends upon, one can say, the present inputs and the current state, which is a result of the previous input. Okay. So that means you need to have some sort of feedback from the output in such form, right? So where the current state is fed back to the input, and then you have a register in between to store that current state. Okay. So and then you also have a clock which is applied to the resistor. So maybe let's say it's a positive edge triggered
Sir,
resistor. Yeah,
sir,
please.
we can't see your PPT.
The PPT is not visible, sir.
Okay. Let me share it once again then. All right. Yeah. So yeah, let us talk about then designing sequential logic circuits. Okay. So as I said that in a combinational logic circuit, the output is only dependent on, I think it is visible now.
Yes, sir.
Yeah,
Yes,
okay.
sir.
Okay. So combinational logic circuit, as I said, that output is dependent on the present inputs only. Okay. And in a sequential logic circuit, for example, this is a finite state machine, or you can call it a sequential logic circuit, because you have a common clock here. So clock is single clock, or a common clock is present over here, which is synchronizing all events in this circuit, right? So in fact, this is a very small portion of a bigger circuit. There could be bigger sequential logic circuit possible, okay, which may have hundreds of such sort of small circuits like this, and all the entire circuit is being synchronized by a single or common clock, right? So a sequential logic is a circuit where the outputs will depend upon the present inputs and also the previous inputs. Okay. Or one can say the output depends upon the present inputs and the current state. So current states now depends upon again obviously previous inputs. Okay. So that means there is some sort of feedback, so that has to be supplied from the output to the input. Okay. Now this feedback, which actually contains the current state or maybe the next state, so that has to be stored in some register over here. So some register may be utilized or some storage element can be utilized here, so that will store the value of the output on the previous inputs. And then when the clock, this is a positive edge triggered register, so obviously it will copy the D input to the Q output when the positive edge of the clock comes in, right? So when the clock makes a transition from 0 to 1 or low to high, okay, or when we call as positive edge comes in, that is when clocks makes a transition from low to high or 0 to 1. So then the D input, whatever is appearing at the D, so that will be copied to Q, right? And in the other scenarios, D will not be copied to Q. So whatever changes are happening at D, that will not affect Q in the other cases. Okay? Only when the clock is making a transition from low to high, that is whenever the positive edge is coming, then only D input will be copied to Q. Okay, so for example, based on the previous state, okay, my output which was appearing at D here, so that is copied to the Q output, and that becomes the current state. Okay. Now the next state cannot come in and change this Q output until the next positive edge comes in. Okay. Until the next transition from low to high that comes in. So during the next transition from low to high, this next state will be copied to this Q, and then finally the output will be calculated based on this current state and the inputs. Okay. So it has two kinds of mechanisms, sequential logic. So they have two storage mechanisms. One is via this positive feedback. This is a feedback. Okay. So positive or regenerative feedback. So some time back we had studied what is regenerative and positive feedback. In fact, during the course of learning sequential logic design, we'll once again talk about the positive and positive or regenerative feedback mechanism. So we'll talk about that later. So, but yes, let us understand that there are two storage mechanisms. That is two storage mechanism by which one can store the current state or next state. So one is via positive feedback. Maybe this is a feedback via some registers. You can store the current state, and the other is charge based. That is storing the next state or current state on some capacitor and then refreshing that capacitor at regular intervals. Okay, so there are two storage mechanisms possible in a sequential logic design, that is positive feedback based or charge based. Now in our discussion in this course, we will assume that a latch is level sensitive, right? So because there is different conventions which are being followed by different textbooks, but yes, when we talk about this textbook, so we'll always utilize this convention, that is a latch is always level sensitive. So we'll say that when we talk about latch, so latch is always level sensitive, and when we talk about register, we'll say that register is edge triggered, either positive or negative edge triggered, or what we call as positive edge sensitive register or a negative edge sensitive register, right? So latch is level sensitive, that is depending upon level, that is 0 or 1 or low or high levels, we'll decide the transition at the output. And register is edge triggered, that is depending upon the positive or negative edge of the clock, we'll decide whether the input is copied to Q or not, the output or not, right? Yeah, so in some other books you will find that edge triggered elements are also called flip-flops, right? But here in this course we will say that the edge triggered element is a register and a level sensitive element is a latch. So let us now define a latch and register. So here is a latch being shown over here. So since the latch is level sensitive, and let us say that this is a positive latch, that is it stores data, that is it stores or copies D input to the Q when the clock is positive. Okay, so that is maybe here we see that in at this point D is held high, right? From here to here D is held high, and when the clock becomes positive, that is level is positive, D input is copied to Q, right? So Q input is copied at this instant, that is when the clock is positive, that is positive levels in the clock are achieved at this point. Okay, so the D input is copied to the Q output, right? So Q is now held high at this point. When Q is positive, D is copied to Q, or Q is also high now, right? Now when D is negative, sorry, when clock is negative, right, and during this region, okay, so nothing happens to my output. So output is still what the previous output was. So output is still high. Okay. Now at this point, you see that D is making a transition, that is D is changing at this point, right? But since clock is still positive here, right? So during this portion, so my Q is also constant here during this portion, right? Now when D is making a transition, during this portion, the D is making a transition. Now in this portion, I see that clock is also positive. Okay, so that means clock is positive since in this duration. So that means my D should be copied to Q, and D is 0 here. So Q is also becoming 0 here now. Right. Similarly, register. So if you look at the register, so this stores data when clock rises. So this is a positive edge triggered register. Now the symbol to differentiate a positive and negative edge triggered register is that you place a bubble over here to say that it is a negative edge triggered register. So if it is a negative edge triggered register, you will see a bubble over here. Okay. Similarly, if you have a negative level sensitive latch, so you will see a bubble over here. So since you do not have a bubble over here, so that means that this register is a positive edge triggered register. So as soon as the clock becomes positive, that is, okay, clock is making a transition from low to high here, these portions. So whatever is the D input during this time, so that will be copied to Q, right? So let us verify this. So D is high at this point, Q is also high. Okay. Now, clock is high here, D is also high, Q is also high. Okay. Now D is low here at this point, but since D is low here, and D is low here. I think this should be, since this is a positive edge triggered, so I think here we should make a change over here. So this should be copied to Q, right? So it should be this much, I think. Yeah. So since it's but there is no edge, so it happens in the case of level sensitive. It's a edge triggered, so nothing will happen over here. Yeah, so nothing will happen over here since it's a edge triggered. Yeah, it's a edge triggered, so nothing will happen over here. Right. So here you will see that these are the positive edges. Okay. So D is making a transition here. Okay. But Q is not affected because this will wait for the next positive edge to come in. Then only the changes will be reflected at the Q, that is output. Okay. So next positive edge comes over here. From here it comes over here. So at this positive edge only Q output will follow D. So which is happening over here. Right. So now at this edge, Q is following D. But at this edge, or maybe in this region, entire this region, nothing happens to the Q output, right? Because it has to wait for the positive edge of the clock. So at the positive edge of the clock, the changes can happen. That is, D can only be copied to Q. So which is happening over here. Yeah, so that is being explained here also. So this is a positive latch. Yes, positive we say because we don't have a bubble over here at the clock, and this is a negative latch because we have a bubble over here at the clock. Okay, so positive latch will copy D to Q when clock is level is high. That is, when clock level is high, that is in this duration and also in this duration. Okay, so it will copy whatever is the input, so that will be the output. So input is copied to the output here. Similarly, input is copied to the output. Okay. And in this case, here, input is not copied to the output, right? Because it is a positive level sensitive. So no changes in the input will be reflected to the output. Similarly, here, it's a negative latch. So it will copy the input, that is D to Q output, only in this region. Okay. So in this region, we see that input is copied to the Q output. Right? That is, output follows input, okay, when the clock is negative. Similarly here, when the clock is positive, output follows input. Okay. Or the clock or the latch is transparent. Okay. Transparent means output is equal to input, or input is copied to the output. Now in a latch based design, one has to also think about this clock frequency. I mean, what would be the clock frequency and how to decide the clock frequency of any circuit, right? So one has to decide the factors which will decide the clock frequency or maybe the clock period. right? So for example, in this circuit, you will see that there are two latches. One is negative latch and one is positive latch. Okay. So negative latch is transparent when clock is 0, and positive latch is transparent when clock is 1. Okay. So that is when clock is 0. Okay. So let's say when clock is 0, so whatever is appearing here at this, so that will come over here. Okay. When clock is 0. Okay. Similarly, when clock is 1, so whatever is appearing here, so that will come at this point. Okay. So that means this circuit works in two phases. That is when clock is 0 and when clock is 1. Okay. So in the synchronous sequential circuits, one would also admit that the next cycle, so that cannot begin unless all computations have been completed in the previous cycle. Okay. So here the previous cycle is, let us say, when clock is 0 is one cycle, and when clock is 1 is, so that is the next cycle. So when clock is 0, that is previous cycle. So in this cycle, my data which is present over here, so that has to be processed by this negative latch, and then that data has to appear over here, and then this data has to go inside this combinational logic block. That is, this combinational logic block will process that data, and then this data will be available here, right? So that is actually one stage, or during one clock cycle, that is when clock is 0, this much operation has to be performed by this circuit. That is, when clock becomes 0, this negative latch has to process the data, and the data has to be available here. Then the processed data has to be again processed by this logic, and after processing, that data has to be available here. So that much clock period I need. So that clock period depends obviously on the delay of this negative latch, okay, the delay of this latch, negative latch, and also the delay of this logic block, combinational logic block, which process my data further. Okay. So that means my clock period depends upon, or my clock frequency should depend upon the delay of this latch and also the delay of this logic. Okay. Now when the next cycle comes, that is when clock is 1. So again, when clock is 1, so this data which is appearing over here at this point, so this has to come out over here, and then this data has to be supplied to this logic, and then this logic has to process this data, and then finally this processed data has to come over here, right? That is this much operation from here to here, this point. So this has to be completed when my clock is 1. Okay, that is, in the next cycle I have to perform this much operation. So obviously then the clock period should also consider delay of this latch, okay, and the delay of this logic block. Okay. So these things have to be considered while deciding the clock period or clock frequency, right? So that total clock period or clock frequency, so that will actually consist of the maximum delay. Okay. So the maximum average delay which is being consumed, the delay which is consumed during the two cycles. So average maximum of the two delays, that is, one delay was when the data was processed from this point to this point. Okay. So that was one delay, and the other delay is when the data is processed from this point to this point. Okay. So the maximum of these two will be incorporated in the clock period. So this is how we decide our clock frequency and or clock period, and then there are many more things, so that have to be added. Okay. So now before this logic block, that is logic has before they have processed the data, the next cycle should not begin, right? That is, within when clock is 0, in that time my N latch and this logic, so that has to process the data completely, and data should be available here. So before that, the next cycle, that is the processing of data by P latch and this logic element, so that should not begin, right? So this is one of the things one has to remember while designing synchronous sequential design, right? That is, one cycle cannot begin until the previous cycle has completed completely, right? So unless the previous cycle has completed, the next cycle cannot begin computation. So previous cycle has completed now, the previous system has also come to rest. That is N latch and this logic element that has to come to rest before this P latch and this logic becomes active and they start processing the data. So that has to be remembered, right? Now, before finding out the actual clock frequency required for any circuit, yeah, not just this circuit, but for any circuit, maybe let us say that we have now this circuit, the same old circuit we discussed at the beginning of the sequential logic design. So let us take the same circuit and try to find out the clock frequency required or the time period of the clock required for this circuit to function correctly. Okay. Now before that, let us also define two more quantities. One is called setup time, right? So which is shown over here, setup time, and the other is called hold time. Okay. And then the third one is clock to queue delay, right? So setup time is time for which the data should be stable before the clock edge comes in. Okay, since this is a positive edge triggered system, so this register is a positive edge triggered register. Okay, so we say that the data D, that is this data, should be held constant for the time before this clock edge comes in, right? So the clock is shown over here. So this is my positive edge here, okay, and here is my data. So setup time says that data should be stable for some time before the clock edge comes in. Okay, so the clock edge comes in here at this point. So this is the point where my positive edge of the clock comes in. So the data should be stable for some time before this clock edge comes in. What time? So that time is this much, and this is called setup time. That is, the data should be stable before the edge, before the positive edge of the clock comes in. So this is called setup time. Okay. So for correct operation of this circuit, setup time, condition. So that has to be, it is mandatory to hold this condition. That is, setup time condition should not be violated. That is, data should be constant before the positive edge of the clock comes in. Okay. Now similarly, hold time. So hold time is the time for which the data should be stable. That is, D input should be stable after the clock has come in. So this clock edge has come in at this point. Now till this point, maybe let us say the data should be stable, and this is now my hold time. That is, the data should be stable for some time after the clock edge has come in, right? So this is called hold time. Okay. Now then we also define another quantity which is called clock to queue delay. Okay. That is when the positive edge of the clock has come in over here. Now how much time this register takes for processing this data input, that is how much time this register takes to copy this data D from input to the output Q here, right? So that is called T clock to Q delay, right? So the total delay, the total clock period, so that required for this circuit to function correctly, so that obviously will consist of now setup time plus the delay of this register, or what we call as clock to queue delay, and also the delay of this combinational logic block, right? So three delays have to be included in calculating the minimum clock period required for this circuit to work or function correctly. So that minimum clock period should be greater than or equal to the delay of this register plus delay of this combinational logic plus the setup time, right? Now this T clock to Q, that is the delay of the register. So this is also the worst time propagation delay, or worst scenario of the propagation delay through the register. Okay. Then apart from this worst case of propagation delay, which is called clock to Q delay, we also have another delay for this register which is called contamination delay of the register. So this is contamination delay is minimum delay of the register, right? So minimum delay of this register is called contamination delay, minimum delay, is called contamination delay, and T clock to Q delay is the worst case delay of this register. Similarly, for this combinational logic block, we define two delays. One is TP logic. So TP logic is worst case propagation delay of this combinational logic block, and we also define contamination delay logic of this combinational logic block. So contamination delay of this logic block is the minimum delay of this combinational logic block. So since we studied some time back that based on the inputs, the delay of the logic also changes, right? Or the input reordering also we studied some time back. That is, depending upon the combination of inputs which are present in the logic, the delay of the logic changes. So worst case delay is called TP logic, and the minimum delay of this combinational logic block is called contamination delay logic. So now this contamination delay of logic and register, so that sets up a requirement on hold time. That is, my hold time should be less than or equal to the minimum delay of the combinational logic block and the
Sir?
register. Yeah, please.
Sir, can you repeat TCD register and TCQ?
Yeah, TCD register is contamination delay of register and contamination delay of logic block. Okay, contamination delay is minimum delay. Okay, and the logic delay is the worst case propagation delay. So worst case propagation delay and minimum delay. There are two things, right? So one has to remember. One is the delay in the worst case situation, and one is the minimum delay. So worst case situation delay can be even more than this minimum delay or contamination delay. So depending upon the situation which is inside this logic block, that is inputs which are fed to the combinational logic inside the combinational logic block. So depending on that, one may have two kinds of delay. That is, one could be minimum delay and one could be the worst case delay, right? Now this hold time, so that sets actually a requirement on my hold time. That is, contamination delay sets a requirement on my hold time. So that is, hold time should be less than equal to the contamination delay of register plus contamination delay of logic. So for example, here if you remember contamination delay here, the whole time. So hold time is mentioned over here, okay, and clock to Q delay. So that is mentioned over here. So clock to Q delay here is greater than hold time. Clock to Q delay again means the maximum delay or worst case propagation delay when the clock edge comes in and when the output, that is D input, is copied to the Q. So that is clock to Q delay, worst case of that delay, right? So this whole time cannot be greater than this clock to Q. If it is greater than this, then this clock period, so that should also include whole time instead of to TCQ. So one could modify this now by saying that T is greater than equal to setup time plus hold time, right? But that is actually not a requirement here. So requirement is that the whole time should be less than these two minimum delays of the register plus the combinational logic. So minimum clock frequency or minimum clock period that is required for this circuit to work properly would be equal to the delay of that should be greater than or equal to the delay of this combinational logic plus delay of this register plus the setup time, right? So this much clock period should be minimum present. If it is less than that, then the output may be something else. Yeah? Output may be something which is not expected if this clock period is smaller than this quantity. So obviously it can be seen from there. Yeah, so maximum clock frequency we discussed. Now let us also talk about static versus dynamic memory once again. Okay. So in a static memory, you have some sort of positive feedback loop that stores data till power is supplied. So we had seen static gates. That is, static gates can also, static CMOS gate can store the data at the output till the power is supplied. So that becomes the foundation for static memories or the foundation for multi-vibrator circuits or bistable elements. That is, till the time the power is applied, the output state can be retained. Yeah? So that is the foundation for bistable elements also and multi-vibrator circuits also. Now for a dynamic memory, you will find that data is stored on parasitic capacitor elements. So that is why the data needs refreshing, because capacitor will lose its charge after some time. So it needs some sort of refreshing in maybe some milliseconds or nanoseconds, depending upon the circuit and the size of the capacitor. Okay. And the important point here you would notice with respect to dynamic memory is that dynamic memories are simpler, they are high performance, high speed, and also they have lower power dissipation, right? But yes, they are not much robust, and also they are not reliable. Now let us talk about utilizing the same concept, that is a positive feedback, in making a memory element, right? So some time back we discussed what is positive or regenerative feedback. Okay? So the same concept is being used here to create a memory element here. So for example, this is my memory element. So one memory element could be this, or maybe you can represent it by another same circuit, but let us say that now the arrangement of inverter is same, but just I have put this inverter, that is inverter number 2 here, that is I have put at the bottom here. So this is a memory element here, right? So suppose you apply some input here, Vi1, okay, and then you cut the input supply, right? So you cut this input supply. So once this gets in, so this input can be retrieved in this loop, right? So this input, once you cut this input, so this input now can be retrieved from this loop. So it is stored in this loop, right? So because you have Vi1, let us say, applied here. So output of this inverter is VO1, which is applied to the input of the second inverter, okay, which is Vi2. And based on VI2, you get VO2, output of second inverter. And this output of second inverter is equal to the input that you supplied to the first inverter, right? So this acts as a memory element, that is whatever input you applied, so that is stored in this loop, right? Or what we call as feedback loop or a positive feedback loops. Yeah? So this is a positive or regenerative feedback loop. Okay? Now there are two stable states here, obviously. So this defines the principles of bistability, that is this loop has two stable states. One state is obviously high state, VDD, and the other state is low, right? That is high and low, both can be retrieved. Okay. Now, if you try to draw the VTC of inverter 1 and inverter 2, and then, overlap by mirroring the VTC of inverter 2, you overlap them. So you get this kind of picture. So this we had seen earlier also. Okay. So this is overlap VTC after mirroring the VTC of inverter number 2. Okay. Now from this picture, one can find out three regions of operation. Okay. There could be three operating regions. One could be A, and one could be B, and one could be C. Right. So C is a metastable region. We say that this C is metastable. Okay. And this A and B. So these are two bistable points. Okay, that is these two A and B. So these are two bistable, points or bistable regions. That is bistable logics, or maybe A is, we would call A as VDD. So two bistable means two stable levels. That is one is VDD and the other is 0. Okay, so two stable levels can be found, A and B. That is VDD and 0, and the other is metastable C. Right now, since I said that this sort of feedback is positive or regenerative, so obviously that means there cannot be, the circuit cannot, if even I try to bias this circuit at the center of this transition region, that is if I try to bias this circuit at this point C. Okay, so after some time you will see that this circuit will either the biasing will change to either A or B point. That is since it's a bistable circuit and it has a regenerative feedback, so maybe because of some noise, okay, so I had biased at this point, maybe because of some noise, this biasing point shift to this point. Earlier it was biased at this point, that is center. Now because of some noise, this biasing point can further shift below. Okay, that is, it can come to this point. Now at this point, if I try to find out the VTCs, that is the response of these two inverters. Okay. So this will be, this will be amplified. Okay. So at this, I'll get this much output, and that this much input, I'll get this much output. So that the output levels are converged to either VDD and low, right? So if I bias it at this point, so obviously the outputs will converge to, B point, right? So it has two stable points only, or bistable. That is, even if you try to bias it at C, it is likely that finally the circuit will land up in two, either of the two stable points, that is A or B. So which I think we had seen some time back also. That is, let us say you have some noise which is affecting the biasing of these two CMOS inverter. Earlier it was biased at this point. Now it is biased because of some noise. It is biased at this point now. So this, since it's a regenerative feedback, so the circuit will, converge back to its nominal level values. That is, it can either converge back to A or B. That is two bistable points. Yeah. So the bias
Excuse me,
point.
sir.
Yeah, please.
Sir, means those bistable points are VOH and VIH, sir.
A and B.
Yes,
That
sir.
is VDD and 0 bistable points.
That
VDD and
point,
0.
that B is called VIH, sir.
If the noise margin is high, so you can call, if VOH is equal to VDD and VOL is 0, right?
Okay, sir.
So A and B are bistable. I mean, two stable points or two logic levels. That is either 1 or 0. You relate it to noise margin. Yeah. So if the high, the noise margin is very high. In fact, here I don't think the noise margin is high in this circuit, because the best case we found that it's ideal where VOH, this kind of VTC if you get. So this is the ideal case where VOH and VOL. So VOH is equal to VDD by 2. Sorry, VOH is VDD. So noise margin at high and low are equal to VDD by 2. Right. So the bistable circuit has two stable points, that is either 1 or 0. Okay. Now this point C, that is bias point C, this will move either to A or B, right? Because C is an unstable point. C is an unstable operating point. Okay. Now a very small deviation from C, that is, which may be caused because of noise also. So if there is some deviation from C, then this bias point can either reach to A or B after some time. Okay. It can never stay at this point. So that is why it is called bistable circuit. That is, it has only two stable states, either 1 or 0. Now, coming on to, making the use of these latches to implement the registers. Okay. So let us try to make use of these latches to implement the registers. Okay. So, one can think about having a multiplexer based latch. Okay. So multiplexer, obviously we understand that depending upon the selection lines, right? So depending upon the selection lines, you have, I have a select line maybe here. I say that this is my select line. This is 0. Let's say this is 1. If select line is 0, right? So the output is, maybe let's say this is A and this is B. So if select line is 0, then output is B, right? If select line is 1, the output is A, right? So based on this multiplexer, so one can think about implementing a multiplexer latch using transmission gates, right? So these are transmission gates over here. So utilizing the transmission gates and the static CMOS inverter, one can think of making a multiplexer based latch, right? That is MUX based latch. And this is MUX based latch. MUX based latch. Okay. So let us try to understand the operation of this latch. Okay. So when clock is high, okay. So when clock is high, so this transmission gate is on. Okay. When clock is 1, so this transmission gate is on and this one is off, right? So when clock is 1, D input comes in from here, okay, and then it goes here to this point, and yeah, from here it takes this path and it comes over here. So up to this point, my D input can come in. So when clock is 1, my D input can come over here and it can come up to this point, right? So D input is staying here right now. Now when clock is 0, okay, so when clock is now 0, so this D input is cut because this transmission gate switches off, okay, and this transmission gate, so this switches on, right? So when clock is 0, this is off, that is D supply input is cut, and whatever was stored, so that now is stored in this loop because this transmission gate is now on. So this looks like a latch which is I think it's a positive latch, that is the D input, it takes the data when the clock is high, okay, and when the clock is 0, it retains that data, right, in this feedback loop. So it is a positive latch, positive level sensitive latch, okay, so which is storing data in this loop when clock is 0, right? When clock is 1, the data comes in, and when clock is 0, that same data is retained in this loop, right? Maybe I'll remove everything here so that it is more clear, right? So when clock is 1, the data comes in here, comes to this point, stays here because this is off. So when clock is 0, this becomes on, and this is off, so the data supply is cut, and now the data keeps on moving in this loop, or the data is stored in this loop. So the data will remain in this loop till the power is supplied to this circuit, okay, since this is a static memory, okay, so the data will be stored here. So this is resembling a multiplexer operation again, because when clock is 0, you're selecting, sorry, when clock is 1, you're selecting the data, and when clock is 0, the data is retained over here, right? So this kind of multiplexer may be, okay. So when clock is 0, the data comes in, okay, at output Q, and when clock is 1, the same data is stored in this loop, right? So this is how a multiplexer based latch can be designed using transmission gate and CMOS inverter. And the output Q, right? So the logic function can be written in terms of clock and Q and the input. Okay? So this resembles a multiplexer actually. Okay. So this is a negative latch, for example, and this is a positive latch. So negative latch here. So because it is sampling the data when the clock is 0. So when clock is 0, the data is sampled. Here, when the clock is 1, the data is sampled. Okay. So that is why this is positive latch. That is, it is transparent when clock is 1, and this is negative latch when it is transparent when clock is 0. Now, similar to this mux-based latch using transmission gates, one can also think about a simpler latch, okay, where you don't have an extra inverter. I mean, one inverter and one transmission gate. So that can be reduced here. So this circuit has now just 2 inverters and 1 transmission gate. So here we had 3 inverters and 2 transmission gates. Okay. So this also works as a multiplexer based latch. Again, you can verify here. So when clock is let us say 0. Okay. So when clock is 0, this is on. So when clock is 0, transmission gate is on. That is, D is latched. D comes over here and also it is present over here, right? So when clock is 0, D is latched at the output, right? So it is a negative level sensitive latch. Now when clock is 1, so when clock is 1, this becomes off. So data supply is cut, and whatever the data was earlier input, so that is stored in this loop.
Excuse me, sir.
So again, that means we have created a memory.
Hello,
So this
sir.
is my memory over here.
Hello.
So the data which was sampled earlier in the previous clock, that is when clock was 0, so that data can be retrieved here in this loop. Okay. So the data supply is cut. Now if any change is happening to the data, that change is not reflected to the output. So that change in the data will only be reflected when again clock makes a transition to 0. Okay. Now there is a problem here in this loop, right? So that problem is that when this transmission gate is on. So the problem is that when this transmission gate is on, so this D, so this is also trying to write the data at this point, and this feedback loop. So this is also trying to write data at this point, right? So this is a problem here. Again, it becomes a ratioed problem. So that is, if you want, this D input to write data at this point, then you have to make this transmission gate stronger than this CMOS inverter. Okay. So that is why you see that here in this picture, this CMOS inverter is small compared to this one. So which reflects that this CMOS inverter has to be made weaker than this transmission gate. Otherwise, this transmission gate will never be able to write the data over here. So D can never be latched, okay, because this will overwrite it.
Hello, sir.
Yeah, please, can you
sir,
speak
time
up? Yeah. Okay, so let us end the class over here then. And if you have any queries, then please, maybe you can post your queries.
Sir,
Yeah, please.
I have a doubt. Actually, at the starting of the lecture, you show the circuit of the domino circuit in which we use the NOT gate for the so that the another
Okay.
inverter cannot discharge. But
Yeah, correct.
if we use the NOT gate, then I think the desired output we don't get actually. We can use buffer instead of the NOT gate. Can you got my point?
Yeah, but then the problem with buffer is that, I mean, during the pre-charge phase, we discussed that the inputs of the next pull-down network, so that have to be 0, right? So the inputs of the
Actually, sir,
next pull-down network.
we are inserting one more which is NOT gate. Then it inverts the input to the second inverter.
Yeah,
which is
correct. So that is desirable there, because we want the input of the pull-down network of the second stage. So that input should be 0, because if it is 1, then that pull-down network 2, so that will also start evaluation. And the output node 2, so that will be now 0. We don't want output node to become 0, output 2 to become 0, when output 1 is making a transition from 1 to 0. So when output 1 is making a transition from 1 to 0, we don't want output 2 to become 0. And to prevent this, you need to supply 0 to the pull-down network inputs of pull-down network 2, right? And now to provide 0 to pull-down network 2 inputs, you need to connect a CMOS inverter from the out 1 to the pull-down network 2 input. So suppose my pull-down network output is 1. So it passes through the inverter and that output becomes 0. So pull-down network 2 input is now 0. So that is what is desirable. So it is desirable to have a CMOS inverter. So otherwise the same situation, same problem, that is out 2 will then discharge until out 2 reaches VTN. So that problem will be there.
Okay, sir.
Yeah. Yeah. Anything else? Yeah. So if you have no queries, then maybe let us end the class over here itself. Okay then. Yeah. Yeah. Okay then. Let us meet tomorrow then. Okay.